Hello everyone, I am Naveen G. As a part of managing machine learning projects assignment, let us discuss how to manage the machine learning application project. We will walk through below points in this presentation. The first point, opportunity evaluation, which covers the project topic, the problem we are trying to solve using the machine learning. Second point, the CRISP-DM business understanding, basically describes the overall process, business understanding, and success factors. Third point is solution validation plan, details out the solution concept and solution validation. The fourth point will be ML system design. We will dive into actual system design and understand the rationale behind the various decisions. And the last point would be potential risks in the production. We'll close by listing possible issues that we foresee and potential sources of these issues and possible solutions. Let's start with opportunity evaluation stage and understand the problem. The problem we are considering here is predict the maintenance schedule for motors. First question to ask is this really a problem? Answer is yes. Let's understand with some background. Motors are commonly used in every industry and are critical elements for the industrial production. Failure of the motors affect the production, which is loss of business. Acting after the motor failure is not an option. Preventive maintenance is the traditional method where the motor health is monitored periodically and maintenance or repairs are undertaken to avoid the failures. Failures within the monitoring period go unmonitored and contribute to costly repairs and the loss to business. Increasing the manual monitoring frequency also increases the cost. Also, the manual analysis of data is not providing the insight into possible future issues. The next question to ask is, can ML solve this problem? ML is good at identifying patterns in large quantities of data. Given sufficient data and right features, non-random data can be predicted. Prediction helps support making decisions, thus helping us in timely predictive maintenance, which is lacking in traditional methods. Existing data can be used along with the proposed additional sensor data to derive the accurate predictions. Feasibility of these are proven with various research data. Next question is, does anyone care if we go ahead and put efforts into solving this problem? The business operation heads or directors do care for the reduction in maintenance cost, better predictions for the preventive maintenance, and overall production process uptime. All these leads to reduced maintenance cost and increased uptime. Our objective is to build the model to predict the maintenance cycle of motors. To create a model, we'll follow the CRISP-DM process, which involves basically business understanding, that is defining the problem, defining the success, and identifying the relevant factors. Then data understanding, data preparation, modeling, evaluation, and deployment. In this presentation, we'll focus upon the business understanding, solution concept validation, model design decisions, and potential risks in production or deployment. Our first step in business understanding is defining the problem. Let's define the problem in detail. Who is our target user? It is the business operation head or director of an industrial production company. What is our problem statement? The model needs to decide 3 months in advance whether the motor needs maintenance, repair, or replacement. So there is enough time for planning. Why does it matter? What is the specific pain? The pain here is motor failure can cause production downtime and it is very costly for the business. Standby motor needs to be planned well in advance. How is this problem solved today? Currently, the manual periodic maintenance or issue-based repairs are performed without clear insight into motor monitoring data. So what gaps are there in the current state? The periodic preventive maintenance without clear insights cost more. Maintenance cost of motors that are running fine, energy wastage due to degraded performance of motors, failures in between the maintenance period causes the downtime. Second step in business understanding is defining the success. Let's define the success. What is expected business impact? We expect to lower the maintenance cost of motors and increasing the production process uptime. For achieving this success, metrics that we will use are, the first one is outcome metric, that is to reduce the maintenance cost on motors. The second one is output metric. We have selected R square, that is coefficient of determination, as a metric. Target values for our metrics are, for outcome metric, we would have 10% reduction in the maintenance cost. For output metric, we would have a R square value of 0.9. The constraints. Constraint we have here is the prediction must be made 3 months in advance so that we have sufficient time for planning. The third step in business understanding is identify factors that are relevant for our success. From the domain expertise in motor field, traditionally monitored parameters are energy usage, which includes parameters such as voltage and current measurement, and vibration, that is accelerometer sensor data. For deeper analysis and preventive maintenance, additional factors are suggested, and those are insulation monitoring, that is monitored using the insulation monitoring device, and current signature, that is the frequency analysis of current waveform. The next important step is to describe our solution and validate our solution concept. We will follow a scientific method of validation process which involves below steps. First, we will formulate the hypothesis about the solution. Then we will test the hypothesis with the users, followed by we'll analyze our learnings from the tests, and based on the learnings, we will decide to continue or pivot. Then we'll refine our hypothesis and repeat till we reach the baseline performance. Our general solution concept, hypothesis about the solution is as follows. We'll collect the data for our identified features, that is energy consumption and vibration data. Then we'll create a simple model identifying the patterns in the data and relationship to the target failures. For local predictions, collect more advanced data such as insulation monitoring and current signature, and create an advanced model identifying patterns in data and relationship to the target failures for long-term predictive maintenance. We'll start with heuristic or simple model and achieve a baseline performance with the factors that user is already comfortable with, and then we'll move ahead with more advanced models. Validation of our solution concept involves below steps. First, we will review the heuristic simple model with the user. We'll explain the relationship between the input features and targets and shortlist the features that give us the most value. Then we'll validate the model prediction generally matches the manual predictions with domain experts. In case of discrepancy, identify any feature addition or removal is required. Then we'll refine the heuristic or simple model till we reach a baseline acceptable performance. Else we'll pivot and start afresh. We will discuss now the ML system design decisions and rationale behind those decisions. ML system design decisions that we need to take are cloud versus edge, offline learning versus online learning, and batch prediction versus online predictions. The first decision that we need to make is whether our ML solution would be cloud-based or edge-based. We will be using a hybrid approach here, that is cloud as well as edge ML. Rationale behind this decision is there are some basic features based on which we need to provide real-time motor health predictions to users locally. This will happen at edge, that is simple models running on the edge. This should happen without any reliance on the internet connectivity. There are some other advanced features and more involved analysis based on multiple motor data that we need to do, which will happen on cloud. That is complex models with multiple motor data. The second decision that we need to make is whether our ML learning would be offline or online. We'll be using offline learning approach. Rationale behind this decision is changes in industrial environment are slow. Our prediction window is in months and we need the data from multiple motors over long period of time to build an accurate model. Put together, we'll follow batch training on the cloud and scheduled model update on edge devices. The third decision that we need to make is whether our ML model would provide batch or online predictions. We'll be using hybrid approach here, batch as well as online prediction approach. Rationale behind this decision is we need online real-time predictions at edge for general health of a motor and batch predictions at cloud for more complex and involved data for predictive maintenance. Let us now discuss some of the potential risks and their sources in the production for our ML system. Possible model issues we foresee are the training serving skew. Now, this is true for any model. Industrial environment changes over time and there are multiple variables that can combinedly affect the performance. Periodic scheduled training is planned at edge as well as cloud to mitigate this issue. Second point is data drift. Based on the motor age and the environment effects on the sensor, data population may shift, which will degrade the model performance. Again, the periodic scheduled training is planned at edge as well as cloud to mitigate this issue. Third issue could be the concept drift. The change in motor technology can cause the concept drift. The predictive maintenance becomes absolute since new motor has new failure modes and a different relationship to input and output. So technology based edge and cloud model customization selection is planned to mitigate this issue. That brings us to end of this presentation. Thank you for your time.